So let's go. So here's what we're looking at, right? What kind of properties your know light has? What kind of properties? Wave properties, right? That's all we know. As far as we know, and before this experiment, they thought that light only had wave properties, right? This is before that experiment occurred. They thought light was mainly wave properties alone. Hey, when is first right? This Sunday, traffic tomorrow. Right? No, when they're bringing in things down to the block.
If you're coming, I will.
Alright.
I get you food. Yeah, I'll get in. I actually have food.
Alright, so the food, let me give you facts, right? So initially before that experiment, they thought that life had wave properties only. But after that experiment, they said, okay, well, in order to explain what happened in this experiment, they had to introduce some other property that light might have. Okay, I mean, it has what? Particle properties, right? And that's where the wave particle duality came in, right? Light has two properties, waves and particles. Right, so what was the experiment? So the experiment was they took a metal, right? And we know metal made up of all these electrons packed together. I mean, all these atoms packed together with electrons in them, right? Right, so we know it has some free electrons in them. And then it had radiation. Right? This radiation hit the metal, and then they recognize at a particular value, they recognize that electrons left. Right? We call those electrons photoelectrons. Right? And this here is the incident radiation. That's okay? So the photoelectric effect is basically radiation hitting a metal and electrons leaving. That's okay? That makes sense, Shivish? Yeah. So in your own word, what is the photoelectric effect? Electrons leave. Right. So of course, there are instances where plenty electrons leave. There are instances where no electrons leave, right? And we're going to investigate all those small things, right? Are you okay with that? Right. So when this experiment happened, right? When this experiment happened, again, all they thought was light behaved as a wave. All right. So observations happened and they could not explain it, right? So here was some of the observations. Here was some of the observations, right? One of the observations was that there's the incident radiation, right? When the radiation hits, they thought that the electrons, well, let me give you the observation first, actually. The electrons left, right, or exited immediately, spontaneously. So as soon as the radiation hits, the electrons left. They couldn't explain why that happened. Here's what they thought. They thought that as radiation hits, the electrons would have built up energy, break the bonds, and then leave. But that did not happen. At particular values, these electrons left one time. They couldn't explain that. Number two, they thought that if they increase the intensity, they thought that the energy of the electrons would have increased. But here's what really happened. When they increased intensity, there was an increase in the number of photoelectrons. Right? Third thing that they observed is when they increase the frequency of the incident radiation. Right? When they increase the frequency of incident radiation. Then they observed that there was an increase in kinetic energy of the photoelectron. Right? There were a few other things, but these are the three that we're going to really spend some time on. Right? Incident radiation. You don't want to write it in the handout, eh? Anyway, go ahead. But those were your three observations. Radiation hits, electrons leave immediately. When I increase intensity, I want you all to understand the concept of intensity, right? Intensity simply means this. If I say increase intensity, all I mean is more radiation. That's all. Okay? That's what increase in intensity means. More radiation hitting it. Right. So when you increase frequency, you recognize energy increases. That's what they had to figure out. They didn't know why this happened. So that's where they had to come up with a new theory of radiation or of light. Right? And who was the guy who put it all together? Einstein. Right? So what Einstein was able to do was use these results and come up with a new way to view light. So what Einstein did is Einstein said, but here's what. This radiation doesn't have wave properties alone. It appears to be acting as a particle. Right? So it's like particles making up a little wave motion, right? So here's what Einstein said. Right? Einstein basically said that the light is waves plus particle. And the particles is called photons. Right, those who now reach, pay attention when you have this. Log in fast. Can't you right to log in? Watch it quickly. Right? I just want to explain it, so you'll be a little lost, right? You can probably do it already, but so watch it. Yeah. Yeah, this is it's looking like it. No, sorry. Right. Ariane, watch here. So what is the photoelectric effect when radiation hits a metal, electrons leave? Right? So we're going to explain it now. Right? So these were the three observations. These were the three observations that wave theory could not explain. That's okay? You done? Right? These are the three observations that wave theory could not explain. So Einstein came along and said that light can now be viewed as particles that we call photons. Right? So imagine this photon here, that's a photon, right? That's a photon there. So what's the name of the topic? Photoelectric. Right, so watch here. Here's the important part of it. Watch up here, Ranju, watch here now. Right, here's the important thing. So he said that it's no longer waves, right? It's made up of particles. And each particle had an energy E, right? Energy E given by E is equal to HF, right? And that H was work done by a guy named Planck. That H is Planck constant. So when you multiply H by F, you get the energy of the photon. Everybody okay with that? Right. So here's what Einstein said. Einstein said that the energy supplied by the photon goes towards breaking the bonds of the electrons, which we call work function, and the remaining energy is kinetic energy. All right, right here. So basically, this is what he said. The energy of the photon coming in when the photon hit the metal, some of the energy goes towards breaking bonds for the work function, and the remaining energy is kinetic. Right, Nikela? Nikela, you can just summarize what it's saying here. Energy of what? Energy of the photons is equal to the energy given off to what? Break bonds for the work function, and the remaining energy is the kinetic energy, right? And this one little formula is able to explain everything here. That's okay? So we're gonna yeah, we want to focus on this, right? You don't necessarily provide here, right? So copy this down now, and then we're going to try to show how this explains everything. That's okay? So this is the summary of everything that we're doing today.
So is it equal to E for H or E equal to
Yeah, E is equal to H. This here.
right? So then what is work function?
Work function is just the energy the electrons need to break the bond. So I'll give you a formula for that. Right? Go on, right? There we go. Hurry up. Copy down that formula, and I want to explain from there. Oh yeah, copy that down. You all ready? You want to do anything on this? Anything on this thing? You push your hand. You push your hand and then you push your hand and see how far you can reach. That'll work, you know. All right, ready now? So again, remember, energy supplied by the photon going towards breaking the bonds of the electron, and the remaining is kinetic energy. All right. So let us see if we can explain number one. Right? I like to use this example, right? I like to use this example, right? So I'll go in Pega later, right? So I'll go in Marshall concert later, right? But to reach here, we'll take a little taxi, and the taxi will cost about $10. $10. $10 right? But to enter you need a little 20, and then to buy a little food and thing, right? Probably a little, right? Right. So nice. So let's say you're on your way here, right? You want to go to the fete, but you only have right? So you're on the way to the cut and you only have $20. Right? What will happen? You'll be able to get in taxi, but when you reach, what will happen?
You don't have enough money to get them.
You don't have enough money to get in, right? So, watch this here.
Yeah.
Right? No, but you can't even get in. You don't have enough money, right? So watch this here. So if I were to give you a photon, right? And the photon didn't have enough energy to break the bond, will any electrons leave? No. But suppose you had a 40. What would happen? You're inside plus you're eating food. That's okay? So therefore, right, we have enough energy to get in, and then we have enough money to get in, and we have enough money for the electrons to leave with.
That'll be $5 basically.
That's okay? So yes. So you will end up with $10.
Oh,
So,
20 plus 10 is 50 and 50 plus 5 is
Right.
25.
So 10 and 20 is 30. You have $40.
Yeah,
that's it, like we have to buy food.
So you can buy rice. So you have two sets of food you can buy. You can buy popcorn and chicken and drink. Right? Right? So basically, if the energy needed, yeah. Right? So if the energy required to break the bonds is 50 joules, the electrons must come in with more than 50 joules, right? That's okay? So if the photons. So if the photons come in with more than 50 joules, right, we will end up with the kinetic energy being the remainder. That's okay? So here's why the electrons leave in one time. Once the energy of the photons is enough, the electrons leave in immediately. That's okay? So that explains instantaneous part here. That's okay? You sure? Right, so Vinay, help me out here. How come an increasing frequency of this incident increasing the energy? Think about it, real simple. Anybody can help him? Anybody?
Basically, increase in frequency.
So we explained number one already. Electrons will leave immediately if they come with enough energy. If they don't have enough energy, nothing happening. If you come with 20 joules, but you need 50, nothing happening. Okay? But how we explain in number three? How come an increase in frequency giving you an increase in the energy? Will this change? That's a constant, right? Yeah.
The energy would have become more
How come?
because the frequency of the I think will get increased.
How come? Because
HF. So when F
right, because E is equal to HF. So if F gets bigger, E will get bigger. And if you have more energy here, you have more kinetic energy here. You'll see that? So this, what Einstein suggests, explain 1 and 2. Right? What about, 1 and 3. What about 2? How we explaining 2? An increase in intensity giving you more photoelectrons. It is a constant, Planck constant.
We can then break it one more.
Huh?
That means what?
Right. Huh? No, that didn't happen. That's what they thought, but that didn't happen. An increase in intensity means more rays, more energy, more incident radiation. They thought this would have given you more kinetic, but that's not true. Right? You will just get more electrons leaving. But I couldn't explain why. My question to you is why. What would happen with more intensity? Right?
the frequency. So
No, nothing. Intensity does not change frequency. Intensity just means more rays coming in. So if every ray had 5 joules, you have more rays with 5 joules. But right, close it. But what the Panchu said is, picture one ray knocking out 1 electron. So if I have more rays, I'll have more electrons leaving, right? But the intensity had nothing to do with the kinetic energy. Are you okay with that? Yeah? So the more rays I have, the more electrons will leave. But if these rays coming in with energy 20 joules, nothing will happen. Okay? And how do I increase the joules? Increase the frequency. Okay? So in a nutshell, that is your photoelectric effect. Right? But as people were asking for some more formulas, we said energy is equal to HF. This is a constant, but also energy required, right? So that's HF naught. F naught is what we call your threshold frequency, right? And kinetic energy is a half mv squared, and I'll show you our next formula why, right? Right? There's a next formula. You all remember energy being Q by V?
Yeah.
Right? Q by voltage. So if it's electrons, it could be E by V.
So, full from 20% of
Yeah, HF naught. Okay? So everything we have here. So everything we have here is for photoelectric effect. So what you need to be able to do is to summarize everything that happened in there. Copy it up? Yeah. A half MV squared.
Hey, so we're up next to it.
Yeah. You don't have. I can remember some things. All right, so this is your photoelectric effect.
Yeah.
I think so.
One thing.
No, I don't want to put my somebody.
I don't want to go
I don't want to. I'll put it up. Look at the eventual. Are you ready? Right, so that is the gist of it. We had to go through the whole story, everything that happened, and all the graphs and things, right?
So basically, with different elements, you have different H values.
No, E is a constant value, different F values. Right, E is a constant, right? Anybody know what H?
6.6.
Ask William, what is the value for Planck constant? 6.63 by 10 to the right? 6.63 by 10 to the minus 30. Huh? Yeah, you give it.
So we use this amount in that.
Huh? No, we talked about wave particles duality. We didn't do this.
But this is a part that you want to use, like where you use like long and like this. Not this part, like
And then everybody okay with that? All right. Before I move on, I just want you to let me see if you all can figure this out, right? Right, so as I said, the formula could also be HF is equal to HF naught plus EV, right? And I'm going to talk about this V in a little while. This V is called its stopping potential. Right. Have a look question, right? Suppose I make you plot a graph of frequency versus VS.
So wait, next one, EBS.
Yeah. I'm going to explain a little bit, right? Do me a favor, right? Use this formula here and tell me what's the gradient and the y-intercept for this. Try that fast. That fast.
Yeah.
Right? What's your lot? Huh? And Nikolai, what you did?
The gradient.
Yeah.
If F is the if F is the y-axis and B is the if F is the y-axis and B is the x-axis, therefore we're gonna make F is equal to whatever plus BS. Oh, we don't do it?
So you divide everything by H.
Yeah.
And you'll get F is equal to E on H VS plus P naught. Sorry, F naught.
Yeah. And that's it.
So F naught is your y-intercept and your gradient is E on H.
Good, now I'll see.
Right? So you see how easily we can take a question like this, turn it into a graphical question, right? All right, let's go to the handout now. Right, two more people, start look at the handout now, please. Aaron, want to read the handout now?
Hey. So, I can have violated my rights. Yes. Hey, so you get on there from the picture last week.
Yeah. All right, take a look at it, please, all you. Take a look at the handout. I want you to read it first, but I want to explain in this version, right? Right? So I wanted to read this and understand, and I wanted to explain to me how the photoelectric effect is applied here. Right, so I'll explain where it being observed there, right? Yeah, we're gonna talk about it.
Right, I think enough videos should do it.
Oh, the last part.
Oh, it's practice. Okay, it's gonna happen. The practice tonight.
Right, why explain what's going on there. Why do you have to move it up?
Because he bonds and he doesn't really work.
Well, right?
Yeah. And then they'll get like a positive charge on each C.
Right, Taylor. Explain how that circuit works in there.
So when light goes to the electron, right?
To the electron.
Well, to the thing that how the rest was.
Oh yeah, previous part. Right, Eden, go ahead. Yeah.
Because remember they say handle and there's something about colors. So if it's a white light is made up of
But so you see, for the white light,
So I was right. I was
so the white light, what might happen with the white light there is that again, it's a little more complicated than done monochromatic, right? You have a little different wavelengths in it. But they're separated and all, there's one beam coming in, so the energy of that is right? But if you would like underwent diffraction and split them up, then some of the ways might cause photoelectric effect and some might not have enough energy. Alright, so here's what happening here, right? Oh wait, what's the experience again? Go ahead now. Wyatt, yeah, Wyatt, right. What are we Wyatt? No, it's exactly what we just talked about here. Go ahead. Yeah. Try and be specific to what happened in there. When the incident creation hit what? Right. When the incident light hit C. Right? The whole thing is the photoelectric cell. The whole thing there is the cell. So when the light hits C, what will happen? No, electrons will while out camera take up right. So when the radiation hits C, it will eject electrons, and the electrons will go to what? Right. And if electrons go to E, there's a what? What potential there? Positive. Positive or negative? No, no, what? E.
Yeah, you're positive. Positive.
No, negative electrons going to E.
The electron.
Right? Electrons going to E, making E negative and what? E positive. Right. So here's what happening now. Right? There's a potential A to C that increases. So you'll see that you'll see remember the formula? EBS. Remember the formula? Kinetic energy is equal to EBS. Right. There's a special voltage that we call stopping potential that can stop the electrons from reaching here. Right? So basically what they kind of doing is applying a reverse potential. And by adjusting this rheostat, we can adjust until the current reading is 0. Right? Until the current reading there is 0, and that special potential is what we call the step potential. Okay, so that is technically what they did in this experiment, right? But let's just run through the notes and make sure we understand everything. So Hertz in 1887 was the first to observe the photoelectric effect during experiments using a right? So was the effect to observe, right. So he used something called a spark gap generator, an early form of the radio receiver. The photoelectric effect was viewed as a process that with light can be used to push electrons freely from the surface of the solid. Everybody clear with that? That's called definition. The ejected electrons are called photoelectrons. Everybody clear with that? Yeah? What are you doing? Pay attention now. Liana here to pay attention to this structure. Right, and a system that Hertz performed the definitive study on the photoelectric effect. He used metal surfaces that were first cleaned and then held under vacuum housed in a evacuated glass tube. And the second plate mounted. So everything he described in there is that cell there. Right? That's the photocell. Okay? And this tube was called the photocell. So on the right hand side there, that's the photocell. So he observed the photoelectric effect in there. Right, the photocell was connected to a circuit shown and then illuminated with light of different frequencies. What is that there again? Digash? Different frequencies mean different what? No. Different energy values, right? So if you change the frequency,
a larger energy.
So different frequencies mean different energies, and the different intensities mean, well, the amount of rays coming in, right? So electrons were knocked out of the metal, and these photoelectrons move freely through the vacuum to the second plate before returning. Right, here's the important part, right? Once electrons move in activity, they will get a what? Current, right? So the micrometer measure the small foot current generated. This value represented the rate at which photoelectrons were leaving the surface of the photoemissive material. Anybody follow what's going on?
Yeah.
So the radiation hitting electrons leaving the current reading. Right? Here's what it did now. There is a potential difference that is set up between the second plate and the negative terminal power supply. That makes sense? Right? Causing the photoelectrons to be pushed back to the photoemissive material. So the electrons getting pushed back the next way now. By increasing the potential difference, the more energetic electrons are further pushed back, and this results in an increase of the a decrease in the current. So here's what it's doing, right? Here's what it's doing, right? Electrons going from here to here. That makes sense?
Yeah.
Right. But because of the battery here being negative, right? There is a reverse potential being set up here. So some of the electrons that don't have enough energy, they're being pushed back in the next direction. Right? So that'll make current value here smaller.
Because that will very push back. That
Yeah,
will back
it's going back to C. That's okay? So not much electrons going back to C. That's okay? What would happen after a while, Divish? After a while, will any more electrons be able to hit? No. And current reading will now become zero. Current will now become zero, but the potentiometer will give you a value called your stopping potential. That's okay? Huh? I got to read this here for you. By increasing the potential difference, the more energetic electrons are pushed further back, and this results in a decrease in the foot current. That makes sense? Right? A further increase in the potential gives a reading of 0. Right? Which indicates no electrons are being emitted by the material. That potential is called the stopping potential. That's okay? So when the stopping potential occurs, if you multiply that by E, you technically have the maximum energy that the photoelectrons will have. The small is charged by electron. Okay. 1.6 by 10 to the minus 9. Okay?
Yeah.
So Azaria, what does stopping potential say again? So what is stopping potential say earlier? The stopping potential is the value of the potential when the current reading is 0. And it's also technically when the electrons at the maximum energy. Right? It can't go beyond that. Yeah. So the electrons, they might be leaving the plate C, but they can't, yeah, they can't go back to plate, they can't go to plate C. Huh? No, they just like cover it. Right? Most right? Most side they don't leave them. So they probably just trapped inside it. Okay, so that is your stop potential. Look at the graph here. We need to understand what this graph saying. Take a little read, and Sean will explain what happening here. What's the those trump? I want to get you here, boy.
I was trying to find
But I live.
all the Trump come out. Yeah, clubs I was on.
Explain it here now. So take a look at that graph. That graph kind of explains what we're talking about, right? If you can explain it, you got the kilowatt time. What does that graph say? Can you explain the graph now?
Like if people are still like Instagram.
All right. So take a look at that. Take a look at the graph. Number one, why is the potential negative?
If you put that B minus B,
B stop here. Why is a minus value?
the T event.
Because technically that we boost potential, right?
Yeah.
Okay. Right. What is because remember when the electrons leave here and reach here, right? And those be the potential difference.
Yeah.
But the is connected to the circuit, there's a potential in the opposite direction, trying to the electrons back down. But that potential.
So when the electricity, let's say it was A in C.
Yeah, see this.
C to A, yeah. So when they from C is a negative potential.
No, to cause it to go back from the back to C, yes, here is a negative potential to change the polarity and it cause the cause no back. Right, Sean, ready? Do your thing. The point where the graph meets in the x-axis, right? Right. Right. So for intense light at the meeting is okay, right? Why are meeting at the same point? Why it is the increase in the intensity, but the stopping potential is still the same thing.
No, but I think so because would be around the same thing. The amount of voltage to reach maximum, maximum like, you know what I mean?
But I want to hear something else. Yeah, you know. We stop will be about why? Because we seen it there, but why constant? Why it is if I change it?
The rest of go to the function.
Close to it, you're getting close to it. What does B stop control? The maximum kinetic, and that gives you an idea of the maximum kinetic energy.
Yeah,
Right? Can intensity affect kinetic energy?
no,
No, right? So therefore, even if I increase the intensity, right, it's still going back to the same P stop. Why is the graph higher? Why is the graph higher here?
because they had to get more current.
Because the higher the intensity, the more electrons leaving, right? And if more electrons leaving, the bigger the current. That's why.
Because that more voltage.
Still stop.
But if that more, if that more current, if it's not more voltage.
No, more current just means more electrons leaving.
Yeah, but that's
Formula for no, that's something totally different. Right? The greater the, yeah, the more electrons leave, the more current. That's why it's looking like that, right? So suppose I wanted to put a medium light, medium intensity. What's the shape of the graph? Right. Okay. Question. Anybody can explain that straight line path? Yeah.
That's like where it couldn't go no more when the voltage still increases.
Right. So already voltage increasing, the same number of electrons leaving. Right? Same number of electrons leaving. Okay, so nice. So two things that's important there. The stopping potential is the same regardless of the intensity, right? And the higher the intensity, the more photoelectrons leaving is. That's okay, Sarah? Right, here, the potential is the measure of the maximum kinetic energy. Remember, I just showed you that, right? Those three formulas there. That's okay. Leonard also found that the intensity of the incident light had no effect on the maximum kinetic energy of the photoelectrons, but more photoelectrons were emitted. Everybody okay with that? Yeah? Thank you. You should log in as yet? You know what's going on? You lost anything, what's it? You lost. Remember Millikan, we'll study him later on as well, right? And when I had done this note, I had tried to put it in chronological order. So from year to year to year, just you'll see what happened. All right. So it went from Leonard to Millikan and then Einstein.
We didn't know that, but we did next year.
What?
We didn't know that, but we didn't know next year.
What?
Guess you want to do that.
No, there's a, you know, that this, it's not everything you need to know. And I condense it so you don't have much extra data. But I just wanted to put it like that. I just like it, right? Robert Millikan later discovered that the frequency of light had a different effect on the maximum kinetic energy, and the frequency below a particular value called cutoff will not eject electrons. Right? Anybody can explain that threshold frequency, D-base? You can explain that threshold frequency there? No.
The highest value, the highest kinetic energy that can happen is the highest frequency. That frequency is affecting kinetic energy, right? Therefore, the highest amount of frequency that can go over the maximum point, that's the highest value of frequency.
So you write to the highest
But the maximum
frequency. Think about it again. Take a little read and think about it again. Read it again. What do you think is the threshold frequency?
the cutoff value.
For frequency, right? That what it would threshold mean, right? Now explain that in terms of what happened in here.
But when the frequency increase, the kinetic energy of the thing also increase.
So the threshold frequency, right? What would happen if you go below the threshold frequency?
They go back to the stop. They go only charge the
Right.
function.
Would the photoelectric effect happen?
Yeah.
No. Right? So the threshold is the smallest frequency that allows the photoelectric effect to occur. Right? And the symbol F naught, right? What is H by F naught again?
H by F naught, the highest value of energy that can be. H by F naught.
H by F naught is the work function,
Yeah.
right? The lowest energy required. Right? Anything lower than the work function, nothing will happen.
Yeah.
Right? If the work function is 20 joules and they go below 20, nothing will happen. That's okay? So the threshold frequency is the smallest frequency required for electrons to be ejected. That's okay? All right, last thing. So here's a graph, and it is explained. Think about it, please. I'll pick up somebody, probably here.
Yes, sir.
Or me, whoever on the book. Huh? You gotta figure it. You got to figure it out. I love it. I actually love it. I love it. Right? I want an explanation for these graphs. 3 metals, energy versus frequency. Yeah, they're all parallel, so they all have the same something. But yeah, that is same gradient, but what the gradient mean there? Wait, so ignore the next two, let's explain one from. What does that graph show you? Which is what? Focus on one graph. What does the graph say? Focus on one of the lines. What does it say? Light up the hit all of the metals. Unaware. As frequency increase the energy when speed, right? So we'll be okay with that. What is the W1? W1 is the work function.
Yeah.
Right? That's the work function, the minimum energy needed there, right? What's the gradient give you?
Well,
Let's say energy over frequency is what? Planck constant. And you see why all the gradients the same? Because they get the same value, right? Okay. Right, so for all photoemitting materials, their slope is the same equal to Planck constant. You'll see now they're right underneath the note. I think here, right? It was also discovered that photoelectrons were instantaneously ejected from the surface of the photoemitted material regardless of the intensity. These observations troubled physicists, troubled the physics world at that time, and that period is called classical physics. So when all this happened on the code, that's classical physics side. When Einstein jumped in, he changed it from classical physics to what we are now calling modern physics here. Right? So he converts everything. Right? And here's where we talked about this during class. These problems brought about what we know today as modern physics. Yes, but I don't. Yeah, she seemed MR anyway. And who else but Albert Einstein was the physicist responsible for shepherding a new era. Right? I typed it. He did it. In 2005, he realized that sorry, in 1905, he realized that light was not behaving as waves but as tiny particles, which he later called photons. Einstein developed on the work of Max Planck, right? And what sort of recognize that there was a big issue back in the time when Max Planck didn't get as much credit that he deserved, right? But without Max Planck, it wasn't going to get easy for THF.
So basically, Planck help Albert. Planck Einstein.
Yeah. And that's what right here. Right? Oh, that's what everyone made. And suggested that the energy of each photon proportional to the frequency, and he came up with E is equal to HS. Right? Here we have everything from classical physics that we talked about, and then modern physics was basically explained by saying that photons make up the waves E is equal to HF, and then we have the Einstein formula there. That's okay? That's everything that we did. So if there's one thing I wanted to gather from this class is this. Right? Next week when it come back, you gotta be able to explain from here. Okay? That summarizes the whole thing. And that fixes all problems as well. Right? In the equation above, E represents the energy of the incident photons, which is the energy required for the electrons to be free. E max represents the max kinetic energy. All right, and all these formulas I gave you, I think I gave you this one on the board as well. Put it in the form y is mx plus c and work it out.
So Mr. I don't know what else always figured right? But like, does somebody see on like the graphs I use?
I'm gonna get 2 years again. Yeah, but then unit 2 years, no, you hardly ever get through. All right. So you might say we will get a graph on this.
Same 90%.
All right, so these are the different graphs. So for homework, I just want you to review, make sure you understand everything on that right hand side there. All right, we'll probably review it via Kahoot or something and go over it and then jump into past papers. So we'll do calculations next year. I don't want to do calculations today. Next day. I don't know.
And next week Friday.
Next week Friday is not a holiday. Valentine's Day is not a holiday. Okay?
You sure?
It's not a holiday.
Okay, you're not gonna go take that. That's why I say.